I think this is fine. All right, I think I left off here. I'm not quite sure, but I think this is where we left off last time in the introductory chapter. I talked a little bit about deep learning and about how it all got started, a little bit about the history of deep learning, of how things evolved, and I think I ended up with some of these memes on the internet on the deep learning that show you that it shows you one thing, that deep learning is a popular topic also among people who are not very math oriented. And this is something that has changed the field of computer vision quite a bit. Computer vision was an area that typically attracted people with a very strong math inclination. Nowadays, in the age of deep learning, where you can download respective code and just run it and train your networks, it attracts people that don't have as much of a math background sometimes, and then they get frustrated if there is any math in it at all. And this is the origin of these kinds of memes. There is a lot of deep learning happening also at TU Munich. For example, in the computer science department, there's a number of professors. There's our group, the computer vision group. We do computer vision, machine learning, and also robotics. And then there's Matthias Niesner's team, computer vision, more graphics as well, and machine learning. So there's quite a bit of overlap. We work on related topics. You know, there's a lot of overlap, a lot of interactions as well. Angela Dai also, she does 3D perception and 3D scene understanding. Then Stefan Günnemann, who does robust machine learning. Then there's Nasir Nawab's team, who does medical image analysis and deep learning in the medical field. And there's many, many more. At this point, almost every researcher is doing some form of deep learning in my experience, and it's quite surprising how many people are jumping on this topic, because there's just so much potential in applying deep networks in physics, in chemistry, in biology, and in material sciences and social sciences, and you name it. Wherever you can learn something from data, that's where you can apply deep networks. This is examples of research that we did. This is a work that we called one-shot video object segmentation, and it's called one-shot because these are networks where you take an off-the-shelf network like this AlexNet, we'll come to that later in class, and you just fine-tune it on a single image of a video, and then you can track, not perfectly but fairly pixel accurately, you can track objects in longer videos, as you can see in all of these results. And you saw in the car example, once the car flips and you see the other side of the car that you haven't seen, then the fine-tuning doesn't work so well anymore. But otherwise it works even in rather challenging videos. And you can see even very fine scale structures can be captured here. Yes. So for every clip, I think we take the first image of the clip to fine-tune. And so we assume we know the segmentation on the first clip, and then we fine-tune the network based on that. And then it's run for the subsequent frames of the video. So this is segmentation. And so you see a little bit, this is a message I've made earlier, is initially deep networks were designed. This is a work we did, it's called FlowNet. It's a collaboration with a former postdoc of mine, Thomas Brox, who is now in Freiburg. And this is PhD students from both of our teams who developed a neural network to estimate motion in videos, or also called optical flow. A very classical image analysis problem that used to be tackled with classical optimization techniques. Why did we do this work? It's obvious. Both me and Thomas Brox, we'd been working on optical flow for decades, essentially, right? So it's a natural thing if you take someone who works on optical flow and hand him a neural network, he's going to apply it to estimate optical flow. And not surprisingly, this worked. And also, if you now look at optical flow methods around the globe, they all go back to this approach. because nowadays everyone is using deep networks to tackle this flow estimation problem. This is work by Laura Leal-Taiché, who used to be a professor here. She was actually a former postdoc of mine. She started the class on deep learning when she was a postdoc with me. I suggested for her to initiate this class, to do a class on deep learning. And this is the origin of this lecture. And she's been here and did amazing research with her team over the years. And she recently moved to NVIDIA. And this is work on multi-object tracking. Again, a work that she's worked on for years. She did a lot of more classical approaches to multi-object tracking, proposed a number of very influential data sets for what she called MOT, multi-object tracking. The MOT challenge data sets is what she basically pioneered with her team. And here she deployed graph neural networks to do this multi-object tracking. So you can see you can apply deep learning in many different areas beyond the image classification case that it started with. Another example from my lab is this is work by Nan Yang and collaborators. And here we deployed deep networks to predict 3D from video. So you are given a video like you see it on the bottom left, a camera installed in a car, you drive down the street, and as you can see, this network is trained to generate a 3D world from a single camera. And so you can drive around. Now this is trained on driving scenarios, so it works particularly well if you drive around in a city. It also works to some extent if you take it in a random environment, but the performance depends a little bit on how similar is it to where it was trained. But it was a significant boost in how accurately you can track a camera, just a single camera, over time. And as you can see in these videos, we can drive around and things typically line up fairly well. This video is cut there much longer. But there's so much more. This, for example, is work by Niels Thuray, another professor here in computer science who is more working in the field of computer graphics. And he deployed deep networks for smoke simulation. The idea being that what he's been advocating, and I think this work is among these, is you typically have physical simulations that tell you how smoke behaves. And those are the ones that you would deploy in Hollywood movies, for example, to simulate smoke in videos. If there's an explosion and you don't want to create a real explosion, as you know, you can simulate fire, smoke, water, everything, and you would then run massive simulations. The problem with that is, in order for them to be photorealistic, they have to be high resolution. And the simulation is very compute intense, especially when it comes to high resolution, large scale simulations. These can be very compute and memory intense. And so what Niels and his team have been advocating is hybrid techniques where you possibly run a simulation on low resolution and then you upsample it to high resolution with a neural network that takes in the simulated low-resolution smoke and makes it into something that is much higher resolution, which is then not necessarily physically correct, but it looks good. So on a coarse scale, it's physically correct, and on a fine scale, it looks good, and that is often sufficient for the audiences. And some of the things that Niels does end up in Hollywood, and some of you may know that he did receive an Oscar for one of his works on, I think, smoke simulation. This was pre-deep learning, but definitely he knows the field. This is also more graphics, image synthesis and video synthesis, where you can train deep networks to basically, take a video and make someone else say the same text. And so you can create video forgery. You know, you can take one person.
And in 2019, the UK will start a new chapter.
Right, and all of a sudden Angela Merkel speaks fluent English. It's amazing. No, her English is quite good. And this, I think, were some of the origins of the startup Synthesia that went into this video synthesis. Here the difference is this is 2D video synthesis, but with time things got more and more 3D consistent and more realistic, and the arms move more realistically, and as you know, also voice synthesis becomes more realistic now. There are several companies offering voice synthesis, and it's quite amazing what you can do nowadays, all with deep networks. Here's another example, Felix Wimbauer and collaborators from our team. This is a deep network that takes in just a single input video, like you saw it in the previous videos, and creates a full-blown 3D world that is not fully photorealistic, but I would say sufficiently detailed and dense that it would enable self-driving, right? And this kind of results show you that just from a single camera, you can capture a 3D world at sufficient precision to enable autonomous driving. It's an important achievement, I think, because there is a huge battle going on between different automotive companies as to whether you need a LiDAR to do 3D understanding or whether a camera could be sufficient. The advantage is many. The LiDAR scanners are much more expensive, and cost is a huge issue in this field, right? So if you develop a self-driving car, and people are doing this, companies are doing this as we speak, and then the LiDAR stack on the roof costs $500,000, the question is, who's going to buy that car? Right? Not me. And then you can say, oh, we'll first make it autonomous and then we'll remove the LiDAR stack. That doesn't work because you built the whole autonomy on the LiDAR, right? If you can get away with cameras, a camera in mass production costs you nothing, like €1 maybe, right? That's pretty much nothing. LiDARs are at least 2 orders of magnitude more expensive, maybe 3 if you want high resolution. And they're bulky. No one wants this thing on the roof. You drive into your garage and you lose the LiDAR on the way, right? I mean, no, yeah. And there's more applications. If you talk about autonomous drones, then weight is a huge factor, right? We've flown even 10 years ago, we demonstrated autonomous nanocopters. These are drones that can fit in the palm of your hand. Sure, you can put the LiDAR sensors on these, but they will not take off because the LiDAR is too heavy, right? But cameras are lightweight, they're cheap, they're omnipresent. So anything that works with a camera is invariably better on these fronts. And the LiDAR doesn't give you much. You know, often people think the LiDAR sees more. No, if it rains, the LiDAR is doomed. One drop of water on the windshield, the LiDAR beam goes through the drop, it gets refracted, you don't get any readout. Or if you have fog, same thing, right? So all the cases where you would think a camera is not good, often cameras are still better. This works in the rain as well, right? No problem. LiDARs do not work in the rain. This is another work by Lukas Köstler, one of our PhD students. It's called Tandem Tracking and Dense Mapping. It's also a neural network-based approach that takes in a single camera, and as you can see, you can create a fairly dense 3D model of the world in real time. And this is actually fully dense. It's a technique that he published in 21 and that ended up getting a Best Demo Award in 2022. Here's more. This is a nice piece of work by Angela Dye and her team, a data set called ScanNet. And this is basically 3D scans that they created with LiDARs to get accurate ground truth scans of office spaces in different places. They use different scan systems, lots of frames, Kinect style scanning, but I think also now more recently LiDAR scanning to get ground truth on the 3D world, so that you can then train your networks to see how well can you reproduce the 3D ground truth. A bit more on, so there's a lot of activities. This is just a few selected examples from research happening in the context of deep networks here at TU Munich. Some connections to other lectures. So there's Introduction to Deep Learning, there's a Machine Learning Basics lecture, Introduction to Neural Networks, more general neural networks. There's lectures on backpropagation, optimization. Sorry, these are different topics that play a role here, not lectures. Recurrent neural networks, so there's different facets that the deep learning lecture touches on. But doesn't always go into great detail on everything. There is other lectures. There's Deep Learning in Robotics by Professor Boimel. There's Machine Learning for 3D Geometry, Angela Dye. Deep Learning for Medical Applications, Advanced Deep Learning for Vision, Machine Learning by Stefan Günnemann, Deep Learning for Physics by Niels Thuray, and a lecture on 3D computer vision that I'm typically teaching in summer. I'd say see you next time. That was last time, so never mind. Yes. Let me, with that, move on to part 2, chapter 2 of this lecture. And I do hope to be staying more in the time frame now. So a bit more about, is this part 2? This looks like part 1. No? 2. So a bit more about machine learning basics. I've shown this this visualization that shows you that AI is a very broad topic, that machine learning, nowadays it's considered part of AI. There was a time 10, 20 years ago when it was not considered part of AI. So when you talk about what is AI, the definition of AI has changed over the years. When I started my own career in this area some 20 years ago, at that point AI was just rule-based reasoning and logic. And I would, for years, I would have told you I don't do AI because I didn't believe in rule-based reasoning and logic. I was more in the machine learning camp and statistical data analysis and all that. But now it's somehow all part of AI, and we live in times when you take a set of numbers and you compute the average. Some people call that an AI algorithm, right? And I've given up arguing that, at a certain level of triviality, maybe we should not call it AI, but I don't care, We live in a time also when if you say you do AI, you get a lot of money, right? So you have an incentive to call everything you do AI. And so that's what people do. And it's hopeless to argue what is and what isn't AI. Let's start with a simple task, the task that actually sparked the whole deep learning revolution, and that is the task of image classification. So here's the task. You're given a set of images, say these, and you're supposed to say, do they contain a cat or do they contain a dog or maybe something else? So let's, for simplicity, say we want a binary classification. Let's say every image either contains a cat or a dog, and you want to say, is it a cat or is it a dog? Or you can say either it's a cat or it's not a cat in the image, right? And what you see already there is this is not an easy task, a task that we as humans solve every day. But admittedly, sometimes it will take even humans a little longer to say, what am I looking at? For example, the black cat on black ground may not be so easy to decipher. Or the white dog on white ground similarly may not be so easy to decide. Is that yours? It is. Yeah. I always take time to find my off switch as well. So it's a challenging task. Why is it challenging? And I think this is important to understand the challenge, the level of difficulty. First of all, cats come in very different shapes, in very different colors, in very different patterns. And very often, you know, I'm sure you've never seen a turquoise cat, right? Still, you look at it and you recognize it, even though the colors are very pink and turquoise. And often you think, wait, but still you can see it is a cat. So even cats that you haven't seen in your life, you will recognize as a cat most of the time. Although, you know, sometimes I see dogs that look more like sheep, you know, the kind of dog. And then I think, is that a dog or a sheep? But then, you know, people don't usually walk around with a sheep on the leash, right? So sometimes you can, you can derive what it is based on context information. If it's on a leash, it's probably a dog and not a sheep. But, you know, and even here, the task is somewhat simplified already, right? Because each image contains one dominant object, right? The real world is typically not like that. You look into the real world, you're going to have 20 different objects in the same scene. And then it's more difficult. So here we've already simplified the task by saying each image contains one dominant object. What is it? Right? But even then, it's difficult. Not just because animals can be camouflaged, white animals on white background, etc., very common in nature. By construction, nature likes to camouflage. But also because there is a projection happening. So even if I know what the cat looks like as a 3D shape, I can see it from hundreds of different vantage points, and every time it's going to look different because there is a different projection of the cat happening. I don't ever see the whole cat, and sometimes apparently cats come in the form of burritos, right? And then it might be even harder to recognize them. And so that makes the challenge difficult. But the aim is to label the images, and in this case, let's say we have two possible labels, blue for dogs and orange for cats, and we want to label each of these images. And this is called image classification. What are the difficulties we have? First of all, we have occlusions, right? So the cat is not fully visible. Parts of it may be occluded by a tie, by glasses, by here a bone or something else. The dog, we only see part of it. The cat is wrapped up like a burrito. We don't see the whole cat. Then there is background clutter that can look similar and can be misleading, so you can't really tell what is object, what is background. But then, you know, we have different forms of cat. If you Google for cat, you get a lot of images of cats, right? But some of them are real images, some of them are drawings or clip art, and then invariably they will look different. And a detector that is trained to detect real cats might fail completely if you apply it to clip art cats. And then you have, as I said, differences in appearance, differences in camera position and object pose, different articulations that the cats can take, different lighting, right? So the whole image changes, and humans are amazingly good at basically taking out the lighting aspects. If you change the lighting in a room, the recognition for humans is hardly affected. They don't even seem to notice, right? For computers, that is not so easy to generate that kind of robustness. So how would it work? We want to take an image, we want to classify it, we want to find some representation of the image that allows us to tell whether this is a cat or not. And that representation should ideally be invariant, meaning no matter in what lighting, what pose, what albedo, what coloring, what background, it should always give you the same classification. So we want to devise a classifier that takes an image and determines, let's say, and in the learning age, what we assume in addition is that we have training data. So let's say we have these images of cats, orange, labeled as cat, and we have images of dogs labeled as dog. So this is a ground truth training data set that we have. And now we get a new image, let's say this little dog here, and we want to know, is this a dog or a cat? So the question is, how can we do that? And there is one way of doing it, and this will be a little bit abstract, where we encode each input data as a vector in a high-dimensional space. For example, what does that mean? You can take all the colors of each image, pixel by pixel, and stack them in a long vector. And then that vector is an encoding of that image, right? And the new image is also a vector in that same space. And if the images have the same resolution, the vectors have the same length. And then you can compute pairwise distances. You can compute the distance of the current image to all the training images. And then you can come up with what's called a nearest neighbor classifier. So you would order, say, these images based on distance to the current image. And then you can say, I will just label it with the same label as the nearest neighbor. You would say, oh, I'm not sure that's going to work. And indeed, it's very shaky. The question is, how exactly do you measure distance, etc.? So there's different notions of distance you can come up with. But if you have a good notion of distance and if you have enough training data, then hopefully the idea is that there is some image that is sufficiently similar to what you're currently looking at, and you know the label of that image, and so you assume that your object has the same label. This is called the nearest neighbor classifier. And if you get this kind of ordering, it would work, right? If that was the nearest image, then that is a dog, then you would label this one also as dog. So, yeah. But you see, in many cases, the next nearest neighbor is already an object from a different class. So if we didn't have this, dog with a bone in the data set, then this method would fail. It would actually classify this as cat, because the cat is then in this kind of ordering the second nearest. And so the issue with nearest neighbors is if you just assign the class value of the nearest one, then you are very sensitive to whatever is the nearest and if you have that in the data set or not. And so you would typically not do just nearest neighbor, but you would do some majority vote. You would take the first k nearest neighbors and then do a majority vote on whatever classes they have, and then assign that class. So here, depending on how you do it, it would either classify it as dog if this is in the image, or maybe as cat if not. And you see this, this can work, but it can also fail. Here's visualizations of it. So you can take all the training data and label it, let's say in here, 3 different classes, blue, green, and red. And so this on the left is the input data with their respective labels. And then the nearest neighbor classifier says that for any point in that data space, any feature vector that describes your given input, you check what is the nearest neighbor and you take the corresponding class. And for the nearest neighbor classifier, this is the class boundaries that you get. So any point, let's say in this red area, is labeled as red, let's say cats. And any point in this blue area, let's say dog images is labeled dog, and maybe these are horses or something, and then any image in this green area is then considered a horse. But what you see with the nearest neighbor is indeed there is one horse, a green one, in the area of red dots, right? A single one. And that affects the decision boundary here. So there is a whole area in the middle of the red area that is considered green. And you'd say, that's not good. I have a single training data that is clearly, let's say, an outlier or seemingly an outlier, and it affects the whole decision process quite massively. Whereas if instead you take the 5 nearest neighbor classifier, meaning you take the 5 nearest neighbors, take their average, then you get decision boundaries that are more compact, right? Then the blue areas here, green, green, red, red, right? So that would be one example classifier called the nearest neighbor classifier. And this is a classical machine learning tool that is surprisingly powerful on much data. And so you would typically not do nearest neighbor because of the very high sensitivity to outliers, but instead you would do a k nearest neighbor classifier, and with larger k you get more robustness. Obviously, there is a caveat. If you take k too large, for example, if k is the number of training data in your data set, then for any point you will always take the average label of all your training data, and that's always going to be the majority class, right? So if you have more dogs in your training data, k nearest neighbor classifier with very large k will sooner or later just say dog for everything, right? And that's obviously not very clever either. But this nearest neighbor classifier is a powerful baseline technique. It's fairly easy to implement, it's fairly easy to understand, and it can serve as a sanity check. You can, for example, use this as a baseline for other classifiers to see how far do I get with the nearest neighbor classifier. And I've seen people arguing that some powerful, sophisticated deep networks do not necessarily perform better than a nearest neighbor classifier. You can ask yourself, how does the nearest neighbor classifier perform on training data, right? Ideally, you would want the classifier to classify the training data correctly, because that data is correct, right? But if you take a k nearest neighbor classifier, then this green dot will likely be classified as red because it's in the red area. Which means you will not, in a k nearest neighbor classifier, the nearest neighbor classifier will always get you a perfect classification on the training data, because the nearest is the training data itself. So, then it will give the right label for the training data. But the KNN classifier will not necessarily give perfect classification on the training data. But so one question for machine learning algorithms is always, how does it perform on the training data? But as we all discussed, there is then the test data or validation data where you want to see what is the performance there. So you train on a subset of your data and you test on a different one. And so you want the method to generalize. And whereas the nearest neighbor classifier works perfectly on the training data, it often doesn't generalize so well to novel images. And K and N classifiers generalize better because there is this additional majority vote happening, that you don't only ask the nearest neighbor, what is your class, and you take that one, but you ask a number, and that way you get a consensus and more robustness on the classification. And so that will typically generalize better to the test data. And then you can ask what you're actually learning with these different classifiers. So let's look a little bit more at the nearest neighbor and the different hyperparameters that you have. The first question is, how do you measure distance? How do you determine the distance in your feature space? Let's say if X is the vector containing the colors of your image, then you can take an L1 distance to some other point C. That means you take the norm You can also take the L2 distance, that is the sum of squared differences, for example. And you can obviously choose different kinds of distances, or you can also fix the number of neighbors, that is another hyperparameter that you can pick. So the choice of distance matters, the choice of how many neighbors will I consult to determine the label. And how do I choose these hyperparameters? This is very problem dependent. And you will typically check how well do different choices perform on my training data, how do they generalize to the test data, etc. And then you have to figure out how do I best choose all of these hyperparameters. And this is where machine learning comes in, that it will give you techniques to choose the hyperparameters in your methods. So how can we tackle this? How can we learn to perform image classification? The task is image classification. We have some data, and from that data we can learn and we can devise a classifier, much like babies do when they learn about the world. Well, first they have to learn speaking, and then you can tell them what the things are, and then they can start learning and can try to generalize. And as I mentioned last time, this is a process that takes many, many years. And sometimes 20 years, sometimes more. Like, maybe at some point in your lives, you will get excited about mushrooms, right? And then you'll want to learn to distinguish the healthy mushrooms from the poisonous mushrooms. And while you may not be able to do that today, if you sit down and spend a couple of weeks or months on it, over books and in the field, then sooner or later you will be able to distinguish different kinds of mushrooms and make sure you don't die. And so even at older age, you can still refine your image classification performance. But with dogs and cats, I suspect you can already do that now. And here's the idea, that in machine learning we have a model, we have an image that we want to label, and then we have parameters, model parameters that we typically call theta, a set of parameters that parameterize our model, such that once we insert an image I, it gives us a label that is dog or cat here. A class label. So here's examples of images and their corresponding label. And then the idea is that we take some of these images in the data set and use them as training data to train the model such that we can then classify these images. And what we typically do for this is we minimize this optimization problem. If you've not seen this before, it will come back over and over in this lecture, and pretty much all of machine learning can be phrased in this way. You're looking for model parameters for your model, and the optimal parameters, let's call them theta star, they are obtained by minimizing what's called a loss function. This is sometimes called a loss function, sometimes it's called a distance cost function, sometimes it's called an energy. There's different terms for it. And basically what you have is you have your label, the ground truth label. Then you have the label that is predicted by the current model with parameters theta for the corresponding image I. And then you have a discrepancy or distance measure that tells you how far is the predicted label from the correct label. And you can imagine these labels could be 0, 1, for example. If you just have two classes, you would take 0, 1. Then it doesn't really matter so much, so you can take 0, 1. And then ideally the predicted label for class 1 should be 1 and for class 0 should be 0, and you can penalize that discrepancy, and you want to minimize that discrepancy, and you want to find the model parameters theta stars such that this discrepancy is as small as possible, meaning for every training data you get the right label. So far so good. If you do that and the model is sufficiently big, you can do what's called overfitting, which means you get 0 error on your training data. It classifies it all perfectly, and then you're super excited and hyped and you take it out into the real world and it doesn't work. And so the challenge that you face is the challenge of generalizing. It shouldn't only classify the training data, but it should ideally also work well on unobserved data. And so typically the recipe that machine learners advocate is the following, that you take all your data, 100% of data, and you split it in some form into training data, let's say 60% of it, validation data, and test data. Now you would say, why should I distinguish validation and test? I train and then I evaluate. But you often have hyperparameters, so you have the model parameters, theta, for your model, but then you might have additional hyperparameters like the choice of distance, etc., the number of, and these you want to determine such that you get a small validation error, and then you can test. And the key idea here is that you split your, say, 80% training data in 60% training and 20% validation to optimize your hyperparameters, such that, and this is the crucial thing, the evaluation on the test set is only done once. Why is that important? That's why there's the exclamation mark. It's important that the test set is always used once only. Why? Because otherwise you start to overfit on the test data. Right? If you keep iterating and keep retraining all your parameters so that the test data performance is good, then you start overfitting on the test data, and then it will not necessarily generalize beyond your data. The truth is more complicated even than that. In truth, there's a lot of researchers in machine learning who deal with what's called domain adaptation, or domain shift, domain drift, etc. There's different terms for it. And this reflects the fact that when you develop your method, you have access to a certain amount of data, but that data may not always be fully representative. This is a big real-world challenge. For example, if I do tumor detection and all I have is my own scanner, say CT scanner, then I will train with images and test with images that come from that CT scanner. And I can devise a method that works super well for that CT scanner. And then I ship it to the US or some other hospital, and they have a different scanner that has different intensity values, that has different resolution, different everything, and then the same method will not work well. Because then the data is not from the same distribution anymore. There is a distribution shift, and you need to account for that. And this takes a lot of headache and domain knowledge to understand what is different about that scanner compared to my scanner. And if you don't understand that, then the method will not generalize. The hope is then again, the better step would be that you collect data from all the scanners from, your colleagues at the neighboring hospitals, right? And get more data together, train an even bigger model, and then it works on those scanners, but there'll be another scanner where it might not work. So you can keep playing this game, and ultimately the challenge is ultimately you will always face cases where the data that you're getting is not the same distribution as the data you trained on. Yes. So typically the model parameters are the parameters that are in the model here that I can optimize for continuously, or that there is a way to optimize them. But then the hyperparameters are the ones that determine the choice of model, because this model is from a particular class of models, and you could consider another class of models. And so one distinguishes there. And so the question is, how can we learn to perform image classification? So we have data, we have the task of classification, and we have a performance measure that tells us how accurately can we classify certain data. And you can distinguish in machine learning supervised and unsupervised learning. Supervised learning is the example I started with, is where you are given a data set of cats and dogs, and someone tells you this is a cat, this is a dog. And as you all know, human learning is partially in that form. That you have parents or friends who tell you that's a cat, that's a dog, right? But most of human learning is unsupervised, in the sense that I would say most of the dogs you've seen in your life, there wasn't anyone who told you this is a dog. You somehow inferred it based on what? Based on similarity, right? How well that works, I told you with my son when he was a year old, and he started learning camel, right, in Egypt, and he was so mesmerized by the camels. And when we came back to Germany, he would call every quadruped, he would call it a camel, right? So, you know, the generalization capacity of humans is so they need some supervision. And in childhood, that supervision is typically there. Someone says, no, that's actually a dog, that's not a camel, and that's also not a camel, it's a horse, etc., right? And with some training data, then humans get better, but most of the learning they do by similarity, inferring that a dog must be a dog because it looks very similar to so many dogs that you've seen. And our classification gets more and more powerful the more we've seen in this world. That is generally true. And so there is learning that you can do from training data that has no label. And that is actually very powerful, and I think there is a big future in unsupervised learning. All the classical deep networks were supervised learning methods, but increasingly the community sees that there is a need to move to unsupervised. Or in between, and there's many terms, but people would typically call it semi-supervised, where you have some supervision but not a lot. So you have training data, some of it is labeled and much of it is not labeled. And so unsupervised learning deals with the case where you have no label or target class, and you need to find out properties of the structure of the data. And so that relates in machine learning to a technique that is called clustering. Clustering is a technique where you're given a set of data points, like in these examples, except on the left, except you have no colors. So that's all the images you've seen, let's say, right? And then you can look into it and say, wow, there are certain groups that I can identify. This group of points is in a similar area, that group of points, that. And then you would say, if points are nearby, they are likely in the same class. I don't know what class that is, but they're likely in the same class, right? And so with this, you can start to reason and infer, at least which points are likely in the same class. How well that works depends on how you embed your input images into the space. And ideally, you want to find embeddings such that the points of the same class end up in the same area in your feature space. So this visualization of points that need labels, this is a very nice way to visualize the learning challenge. Right. And there's a lot of powerful clustering techniques, for example, k-means clustering, etc. We've also written papers on deep clustering, so clustering in the deep learning age. And so unsupervised means you are given a set of images. They don't come with a label, but possibly there's a certain similarity between objects in one class versus objects in another class. And then you can say, can I find a separating hyperplane that separates one class from the other if the assumption is there's only two classes? If someone tells you this data set contains cats and dogs, can you tell me which is which? You can try to find a classifier that separates one from the other. Obviously, even if that works, you wouldn't know which one is dog and which one is cat if no one tells you the label, right? So typically, in order to give it a semantic meaning, you need at least one labeled data. But you can say here are some that are similar and that I mark with crosses and others I mark with circles. And so in human learning, there's a lot of similarity. As I said, you have supervised learning, where you have some teacher, some oracle that tells you what is true and what is not. And you just hope that they know what is true and what is not. As you know, not all teachers are right about everything, including me. And then there's this unsupervised learning, where you infer information from similarity between data. There's also this philosophy of reinforcement learning, where you have agents that act in an environment, something that is extremely popular in robotics. And the idea is that there is some interaction that the agent does in an environment, and based on its interactions, it will get some reward. What that could be depends. For example, a very powerful strategy was to train neural networks to play video games. And this was a popular thing for many years, where you would take video games of the 80s, and that works super well to do reinforcement learning. Why? Because you have a score, and you can take that score as a reward function, and you can train an agent to act whatever way so that the score is maximized. And that works quite well because, and this reinforcement learning works so-so, but it works particularly well if you have an instantaneous reward for an action, because then you get a direct feedback. This was a good action. You just shot the opponent, and so you get a point, and then the system can learn, okay, I'm just going to do that again if that's what gets me extra points, right? It's much more difficult for a game like chess. Why? I like to play chess, but the tricky thing in chess is you move one piece, you have no clue whether that was a good move or a bad move. And 30 moves later, you're dead, and you are not sure what was the move, why I died now, right? So some move you make now might have an effect 20 moves down the line. And that's then very nasty for reinforcement learning, because you don't have an instant reward. You don't have an instant feedback. You get a feedback at the end of the game, and it's binary. You won, you lost. And then you can propagate this back to the 20, 30 moves you did, and you can wonder, and once you lose in chess, you've experienced that, right? You sit there thinking, why did I lose? What did I do wrong, right? And you can't remember any specific move that was seemingly not right. It's just that aggregated, in the end, you just lost, right? And these games are particularly nasty for reinforcement learning. So better something where you have a score that continuously moves up and down depending on what you do. That's much better. So let's start with this problem of classification with a simple linear model. Linear models are not super powerful, so it means you have some feature space where your input objects live in, and let's say you have two classes, triangles and circles, and you want to find a linear hyperplane that separates ones from the others. Obviously, this is not very powerful, and we talked about this XOR case last time. That was a nuisance for linear classifiers. So sometimes you have cases where, you know, you have some dogs that live in this part of space, some dogs here, some cats there, and there is no linear separator that separates all the dogs from all the cats. So here, let's say this example is a simple one where a linear classifier works, but as always in science and also in machine learning, it's good to start simple. So let's start with a linear separating boundary, a linear classifier, and we'll talk about more sophisticated non-linear classifiers later. In fact, we'll make it even easier. We'll not start with classification, but we'll start with what's called regression. Regression is essentially model fitting. So here's the point. Let's say I have an inputs, they live in a space X, and I have an output, they live in a space Y. And so here are my training data, input and output X, Y coordinates. And now I want to fit a function to this data that tells me how does Y depend on X, right? And there again, you can conceive of many functions, but we'll focus on a linear function. So a line that we fit through data, something that is in principle super trivial, but it is the basic of all machine learning, the starting point, basically, if you will. How do you do that? Well, you have your training data, X coordinates. This 1:n means X1 through Xn, Y1 through Yn is the output. And then you have a learner that learns model parameters theta. That's the general machine learning paradigm, right? Input could be the image, for example, of a cat or a dog, and the output could be the label cat, dog. Except, as you saw in this example, these Y coordinates are real valued, not binary, but real valued. We'll come to binary in a second. So here, Y is real valued. And the idea now is that in the training, we have this training data, we learn a model, and then we use this model to label the test data. So we get at test time, we get xn+1, the new image. We get the model parameters, theta, that we learned in the training phase, and that gives us a prediction for y, the value of y. This prediction we'll call y hat, so it is not the correct label, but the label generated by our model. Right, so please distinguish the little hat here on the y means this is the label that the model generates. It's not the ground truth label because xn+1 doesn't have a ground truth, or we don't know it. It has one, but we don't know it. Now the linear model, as it says, it looks like that. Y is a linear function of x, so you have a linear combination of the x coordinates. And since these are vectors, we have this linear combination. So xij is basically the j's component of the input vector xi. And then we weight that with theta j, and we sum it up over the dimension of our input space d. So from 1 through d, d is the dimension where our images live in. And if you write it out, this is what it looks like. So you can write it like this. You typically have what's called a bias, a constant offset in this visualization. You saw it here. The bias is basically at x equals 0, what is the value where it crosses the y-axis. That is your bias, right? At x equals 0, you get theta 0, and then xij, theta j. And in practice, what you do is, so this here is the bias, theta 0. This is called model fitting, and in particular linear regression, because we fit this linear model to the data. We'll come to how this fitting is done in a second. Why is that useful? For example, let's say you want to predict the temperature in this room, right? And you may not have a thermometer, but you want to devise a machine learning technique that can predict the temperature in this room. So you might say, well, it depends on many things. It depends on the outside temperature. If it's hot outside, likely it's going to get hotter inside as well. It might depend on the level of humidity. It might depend on the number of people in the room. If you have more people, it might get warmer, right? And it might depend on how much sun exposure do we get. If the sun enters or not. If it enters, it might get hotter. So these are all factors that affect the temperature in this room. And what we do now is we say each of these factors, let's say we can measure them, x1, x2, x3, x4, and we want to infer, given all of these factors, how does that affect the temperature in the room, and we want to create a model that would allow us to predict the temperature in the room. Something you would always do, right? If you design a building, you have to do these kinds of things. Why? Because you don't want to design a building that constantly overheats. And if you do these models, you can try to predict how different factors will affect the temperature in the room. And so what you would do in a linear regression case, the question is it linear? Let's assume for simplicity that the linear dependency is a good one. We have weights, theta 1, theta 2, 3, 4, that tell us how much does this affect the room temperature here. And there's different ways to predict building temperatures, right? I can go, a physicist might do that. You can go back to first principles, and learn about heat conductivity and learn about how the sun hits the roof and how the heat on the roof dissipates and propagates into this room. It's super complicated, right? And a much easier way is that you just learn the functional dependency from that data. And given enough training data, you can hope that this is going to work, and it's going to be much faster than simulating the heat diffusion through the roof and through the walls and whatnot, right? So here you see a little bit the power of machine learning. Rather than simulating reality, maybe we can just learn it from examples, and that might be sufficiently accurate. And this is an important question when you study nature and model nature, and a lot of science is about modeling nature. The question is nowadays, when do you do physical simulations of reality that are compute and memory and runtime intense? And when do you rely on training data and learning paradigms? And this cannot be said in general. It really depends on what problem you're looking at. Sometimes physical models are important, sometimes learning is sufficient and can be faster. Because in the end, you don't really care how the heat enters this building, how it propagates to the roof. All you care about is the average temperature in this room, right? And if that's all you care about, then machine learning might be sufficient. And so here's how you would go about it with a linear model. And typically what you would do to tackle this problem is you would take training data, you would train a linear model, you would evaluate on the validation data and see how well it works, and then you would maybe revert to a more sophisticated model than a linear one to see whether that gives you better predictions. And so you iteratively tackle the approach of finding the right model with the right parameters to solve your problem. And here's how it is. So I said that the temperature I measure or predicted by this model, given these values of outside temperature and whatever else, I put the weights, I multiply with the weights, I add this offset, the bias. And in fact, what you can do, and this is often done, is you add this bias also to this weight vector. So you have a weight vector that has d plus 1 weights in a d-dimensional space, and the additional one is the bias. And this bias is just multiplied by 1 here, so that creates this additional offset. Why do you write it like that? Because then you can just write it as a matrix vector multiplication, right? So you have a matrix of the input values from one d-dimensional input for n different measurements, and you have the temperature measurements y from 1 through n, and they are linearly dependent. This is kind of the assumption in this model, right? And so given the input features, the temperature or whatever, outside temperature, humidity, you name it, given the model parameters, I get for each of these sets of values a prediction for the temperature in this room. And I can do that for many different settings. So for example, maybe I have 2 measurements where I get the temperature in this room predicted with this outside temperature, humidity, bias, etc., and then these model parameters. If you have model parameters that look like that, for example, and you can already read off something by these model parameters, so this linear model is rather intuitive. It tells you, for example, that here, according to this model, the humidity in the room has no effect on the temperature because the humidity value is multiplied by 0. So it doesn't matter what it is, it will not affect the temperature prediction. Whereas the blue one here, that is the number of people in the room, has a very significant effect on the temperature in this room. And so these weights tell you how important are the different aspects to your prediction. Right, and then you would say, for example, in one case, this is the case where it's rather warm outside, sun is shining. This is the case where it's rather cold. And then you would get different predictions regarding the temperature in this room. And obviously, now that you see all of this, one factor that you would take into account is the setting of your heater. Because obviously in winter these buildings are heated, and so we should take that as a parameter in. And this is something that as a modeler you need to do, right? You need to think about what are the aspects that have a potential impact on what I care about. And if you know these buildings can get heated or air conditioned, you should better include the settings of the heating and the air conditioning into the model. So from the data you can infer model parameters, and that gives you an estimation for a certain set of data. And then if you have ground truth, you can check, does my prediction, my model prediction for this data, does it match the ground truth? Does it match the actual measurement? And this is where you need ground truth. This is where you need supervision. So for different times of the year, you measure the outside temperature, you measure the humidity, and you measure the temperature in this room. And that is your ground truth Y. So that is the correct temperature. And obviously, you want a model that predicts the correct temperature. And so in order to enforce that, you bring in a loss function that penalizes the discrepancy between the prediction y hat and the ground truth y. And the key idea of learning, and this is now the key paradigm in all of machine learning, is that you can optimize the model parameters so as to minimize this loss function, right? So the challenge being, find the right model parameters theta that I get the best model fit. And this is done by optimization. And so machine learning takes into account 2 aspects. One is a loss function that measures how good is your model prediction how far is it from the ground truth, from where it should be. And then, and it also tells you how you have to change the model parameters in order to make the fit better, right? Because I can modify the parameters and see how does that improve my fit. And then you have an optimization algorithm that actually changes the model parameters so as to minimize the loss, so as to improve the estimation, to improve the model fit. Here's an example, linear regression. So I fit a line through a set of data points. So I have some prediction, for example, the temperature in the building as a function of my input space. Here the input space is one-dimensional. In practice it could be higher dimensional, right? That doesn't really matter whether X is one-dimensional or has many dimensions. The difference being if X has 2 dimensions, for example, then you would not be fitting a line, but you would be fitting a plane, right? But same thing. And so you have some discrepancy measure that says the prediction should be close to the training data, right? And here you see already, if you take a random function and fit it to the data, you can perfectly fit the data. If you can just, draw a hand-drawn curve that goes through all your data points, right? That would give you the perfect prediction on your training data, but it would typically not generalize well. And the key idea of linear regression is that we make an additional assumption, and that is the assumption of linearity. That there is a linear dependency between input and output. If that's a good assumption, I don't know, depends, but it's at least some additional assumption that will regularize the problem and make sure that it generalizes and doesn't overfit. And you can see one issue already, right? Here these points are roughly on a line. So if you look at these points and you see they're on a line, then fitting a line makes sense. But, if this first or second point was up there, right? Then that might dramatically affect the line fit. And then you would end up, if you fit a line through these points, and you say, well, this point has to be explained as well by the line, then that will create a very drastic distortion. And this shows you a little bit the issue of what's called outliers. In machine learning, you would say all these points lie on a line, but there's one point that's clearly far away from the line. And if we ignore that aspect and just take it into the training data, and maybe this was wrongly classified. Maybe this is a dog that was for some reason labeled as a cat. And that can deteriorate your classifier if you get incorrectly labeled data that is not correct, right? And so sometimes you may want to devise algorithms that are robust to outliers, that basically fit a line even though there's a few points that are not well explained, so that you don't get this issue. So, the issue being that in order to explain that one point, the explanation for all the other points gets distorted. And you can actually control that a little bit by the choice of loss function. Here, for example, the loss function that we will use is a very simple quadratic loss. So we will say the prediction for data point I is yi hat. The true label is yi. And now we just penalize the least squares difference. So for each point I, we want the quadratic difference to be minimal. So the sum of squares difference, if you want, between the vector yi and the vector yi hat. That is the loss function, and this loss function depends on our parameters because the model depends on the parameters, right? And so by minimizing this objective function, loss function, energy function, cost function, whatever you want to call it, there's many names in the community. By the way, the reason why things have multiple names is because they were invented by multiple people more or less in parallel, right? That's usually why things have multiple names, is because many people invented them. For example, and you can tell typically by what terms people use, you can tell where they come from. Like I would have traditionally called this an energy, and that would tell you my background is physics. In physics, people talk about energies. If you are more in, let's say, management or in business administration or something, you would talk about loss or cost. Right? But then things get blurred with the years. You talk to different people and then you adopt whatever terms are currently most prominent. So this is called linear least squares fitting. I fit sum of squares, and this is a convex problem. Why is it a convex problem? Well, y I hat is linear in the model parameters, and then if I square it, I get something that is quadratic. And that is good because if it's quadratic and convex, there is a closed form solution, a unique optimal set of parameters to minimize this discrepancy. N is the number of training examples. Here, as you can see, I plug in my linear model. I said y I hat should be xi times theta, right? And so as a function of theta, this is quadratic. I can convert that to matrix notation. We will often use that in class because it simplifies a little bit the notation. So X is now a matrix that consists of all the input vectors. All my input images, I vectorize them, say the colors of your input image as a long vector. And then I have a set of images, so this is an n by d matrix, right? Theta is a vector, a d-dimensional vector. And y is also an n-dimensional vector because I have n training data with n labels, y1 through yn. And so this is a matrix vector product minus a vector transpose vector. This is how I can write this out. And these are my labels. But there's going to be more on matrix notation in the next exercise session. So this is important that you gradually familiarize yourself with this form of matrix notation. It's not very profound really, but it's a way to write things more compactly. This is a quadratic loss function, as I said. So in particular it's convex, so it has one optimum. And moreover, how do we compute this optimum? How do we determine the best weight vector for my loss function that minimizes this loss? This is something you might remember from high school, right? That if you have a function and you want to determine its minimum at the minimum location, the derivative is 0, because the derivative tells you something about the slope of the function. And at the minimum, you hit a 0 slope. The tangent is horizontal, and so this is given by dj by d theta equals 0. If you have arbitrary loss functions that can oscillate, you might have many locations where the derivative is 0. But if your loss function is convex, there is exactly one point where it's 0, and that's at the minimum, the single only minimum. And so there is an equation. And in fact, if your loss function is quadratic, then the derivative of a quadratic function is linear. Surprise, surprise, right? And so if you take this derivative with respect to theta, you can do it. Here is theta. If you take the derivative here, you get this expression. And then you can solve this for theta. You have this matrix X transpose X. And you have X transpose Y is a vector. And so you just have to invert this matrix and apply it to the right-hand side, and then you get X transpose X inverse times X transpose Y. That is your solution for the weight vector. This is going to be detailed in the exercise session, but it's really, you know, you have a quadratic function, you set the derivative to 0, you get a linear equation system, and you solve it. And so mathematically you can say we found an analytical solution to a convex problem. Analytical means you can write it down in closed form like you see it here. This will not be the case in most machine learning techniques that you will work on in your lives. In the real world, things can typically not be solved in closed form. We always love closed form solutions, and if you can find a closed form solution for your problem, you can publish a paper and you get a lot of visibility. But in the real world, most problems have to be solved numerically, which means you run some iterative solver that finds an approximate solution. But here, life is easy, life is beautiful, we get a closed form solution. So X again were all your inputs, outside temperature, number of people, humidity, you name it. This is the true output temperature of the building, and here you get your model parameters that make the perfect fit in this least square sense. And then you can start predicting the temperature in the room, and you might find it actually works quite well. And you might find you don't need to simulate heat conductivity through the roofs, through the walls and whatever to get the temperature here. Whether this learning-based paradigm works for your application or not, I said it depends. It also depends on how easy is it for you to get training data. For example, for this room temperature prediction, it's super easy, right? You spend, several times a year, you come in, you measure the temperature in the room, you measure outside. That's easy peasy, right? But there are certain things in the world where getting ground truth is just very difficult. And then, getting enough training data to solve it with machine learning may not be the method of choice. So it really depends. And very often the application of machine learning hinges on you figuring out how can I get massive amounts of training data efficiently. Especially in deep learning, like for fitting a linear model, you can see it already in these examples. Some 20 data points are enough to fit a line. And when you get 30 data points, the line you would get is practically the same as what you get with 20 data points, so you don't need a lot of training data. Why? Because it's a linear model. Linear models a line has basically two parameters, the offset and the slope, right? That's it, right? And to determine two parameters, you don't need thousands of training data, right? But when you come to deep networks, we'll see that this is related to what you could call a shallow network in a bit. But when you come to deep networks, they have lots of model parameters, and then you need more training data. And then you need to think about how do I get my training data fast, scalably. So far, so good. Question is this the best estimate? This least squares estimate? We'll talk about a technique that also comes up a lot in machine learning. It's called maximum. Are we going to talk about it? It's 3:30 already. In 2 minutes? I think not. We'll continue next week. Because this is a bigger chapter and I don't want to start this 2 minutes before the end. So we'll pick up here again next week. Thank you.